Yeah, good afternoon. And so I'm Hao Hui from Hortonworks, and I'm going to talk about scaling HDFS to manage billions of files. So this is a joint work done with my colleagues at Hortonworks. So here's a little bit about myself. Okay. So I'm an active committers and PMC members in Hadoop, and I got my PhD in computer science from UIUC since at 2013. Then I joined Hortonworks right afterwards. So now I have around 250 commits in Hadoop. It's like, yeah, it's like, well, probably not much, but still many. So another speaker, probably he won't be able to come today, and it's pretty have similar background to me. It's still a HDFS team member in Hadoop as well, and Hortonworks as well, sorry. So the story of Hadoop since its beginning is all about the scale of the data. Sorry. So in 2007, a typical PC would have like around 500 gigabytes of hard drive, and it usually contains 1,000 of files. So when Hadoop came out, the most valuable point of Hadoop, is it actually can combine multiple PCs and make it a single logical cluster. Keep jumping. Probably need some help. Okay. So a single Hadoop cluster in 2007, it can contain help. Need some help, I guess. Some interference happening.
Just say yes.
Okay. Good point. All right. Yeah, things don't work as expected, I guess. So can I go next? That's curious. Next, 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 next. Here you go. So, yep, so at the 2007, thank you, a Hadoop cluster contains several hundred nodes. It will manage several hundred terabytes of data, and it has millions of files. So at that point, we are able to say that we can run large-scale computations that scale beyond a single PC. Actually, not working. Anyway, can I say next? Yeah. So we are still making pretty good progress in 2015. So one of the larger clusters in one of our customer bases have 4,000 nodes already. It contains 150 terabytes of data. It managed to have 400 million of files. That's quite a big achievement since 2007. If you look at the metrics we are doing actually orders of magnitude better in terms of scalability. That's weird. Can I go next? Yeah, so what we are doing today from a HDFS point of view. HDFS is translating from a MapReduce-centric file system to a generic storage system. Go next. Yeah, keep going next. Yeah, go next, please. So we have a lot of new use cases. I mean, one of the most important use cases is SQL and Hadoop, Hive, Impala, etc. And people also run Spark as machine learning and do real-time analytics, use Storm to stream the data into HDFS and store them reliably. And in some use cases, Hadoop actually start replacing the filer appliance in the traditional enterprise. People start deploying NFS gateway and to pump data into HDFS. Next, 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 next. Okay. So what's the future of HDFS? So as we can see, the trend of scalability will continue to grow. The cluster is going to be larger, larger, and larger. And we'll have new use cases like Internet of Things, we are going to store time series data into HDFS. So one thing that I would like to highlight is files are actually natural abstraction of your data. If you have more data, it's obvious you're going to have more files. It's just a natural abstraction there. So, however, we are moving away from the map-reduced area and towards a generic storage, which means that we have way many small files in HDFS. So I anticipate there will be billions of files in a few years. Next. Okay. So why this is actually important, and what does it mean for today's HDFS? So just quickly recall the architecture of the HDFS today. We have a master-slave architecture. That basically means we have a really simple one. We store all the metadata in the name node. And then we spread all the actual bits across multiple data nodes. It's really simple, really robust. It proved to work really well since 2007. The problem is it does not scale beyond the size of nano heap. So we caught it in one of our larger clusters, which has 400 million of files. It actually takes 128 gigabytes of heap. So not only buying that much amount of RAM is actually expensive, but actually handling things like GC pauses is actually one of our nightmares in terms of support. We are constantly seeing like GC pauses, tuning GC issues. We just have to wake up and actually get asked by our customers saying that why my name node stops. And this is kind of the answer we have to give. Can I go next? Next. Yes. Furious. Next. Is it that hard? Go back. That's too far. Next. Go next. No thanks. Yeah, go next. Stop. Okay, here we go. So what we are talking today is we are actually thinking about the next generation of the architecture of HDFS. So we're proposing to implement the namespace on top of a key value store. So think of it in that way. In general, is a way to solve the scalability problem in the big data way. We are talking about, because the key value store actually scales out naturally. And what we are particularly talking about today is to store the namespace into level DB. So level DB is using the LSM data structures, which means that you can have a working set and you have a code metadata that can be stored on the disk. That actually matches the usage pattern of HDFS pretty well, because most of the data in HDFS are actually code. The adoption cost of this new architecture would be really low. It would be fully compatible in terms of API, so there's no changes from the application point of view. It just gives you the ability to say that, okay, now I'm able to manage billions of files. Next. So in the rest of the talk, I'm going to talk about how we actually do that and how we actually encode the namespace on top of a key value store. Then I'm going to talk about a little bit about evaluation. And finally, I will talk about the future work and then conclude. Next. Okay. So in order to implement the namespace on top of key value pairs, so the first thing we need to do is actually how to encode the information as the key value pairs. So we store two types of mapping into the KV store. The first one is maps the inode ID to the flat binary representation of inode. So which means it's like things like inode ID, flags, permissions, etc. That gives you the basic information of files. So the second part is models the parent-children relationships. So for PID full actually maps to the INO ID of the child full, whose parent is INO ID is PID. Can I go next? So next. So here's an example. So we got a really simple directory hierarchies. We have a root, and then the root have a child called foo, and then foo has a child called bar. So the right part of the slice is the actual content of the key value store. So the first 3 rows records the information of the inode. So the last 2 rows basically saying that who is the parent, who is the child. So for example, 1 foo maps to 2, which means that the inode number 1, which is the root, has the children foo, and the INO ID of the children foo has the INO ID 2. So based on the table, you can get all the information of the directories. Can I go next? Next, next, next. Yeah, next, 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 next. Okay. So here's how it works. Let's say we want to access the path /foo/bar. So the first thing, obviously, you have to look at the slash, which is the root, which has the INO ID 1, basically is by contract. And then from INO ID 1, and we query the key value pair saying 1 foo, basically saying, do I have a children named foo? And based on the table, the answer is yes, you get the INO ID 2. And then from there, you got 2 bar, because basically it's saying that from my INO foo, do I have a children bar? So that's the query in the red shown on the slides. And according to this table, the answer is still yes. So it got the INO ID, as a result, it got the INO ID 3. So based on INO ID 3, HDFS can continue to query the key value store and get all the required informations. Next, 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 yes. So here's another example of listing directories. So let's say we want to see all the children of the root. So the first step, obviously, is actually resolving the path. So for this case, the INO ID would be equals to 1 when you actually resolve the path. And then HDFS have to issue a range query, basically saying that, asking the key value store, please give me all the key value pairs that have the following pattern, 1 star. So in this case, basically there's only 1 entry, 1 foo. And then based on the information, obviously, because 1 foo is equals to 2, then it query the key value store again, look at the INO ID 2, then it get the information. Can I go next? Next, next. So that's basically how things works. Obviously, HDFS has a lot of existing features that we would need to actually make it happen in terms of a key value store. So I picked 2 examples here. One is the HDFS Snapshot. HDFS Snapshot is a metadata-only operations, so it only happens on the name node side. So in order to implement HDFS Snapshot on top of the key value store architecture, we'll need to tweak our keys a little bit. We need to add a version ID of each key, which is really similar on how LevelDB actually implement their snapshot. And then we will need to map these HDFS snapshot ID and the version ID in the key with a different mechanism, which can be also implemented as part of the key value store interface. So the second feature we need to integrate is the name node high availability. So name node high availability basically means that you have an active name node as a standby name node, and when one name node is down, the other name node can always come up. So in order to do that, they have to have exactly the same state. So in this case, we are basically saying that we can continue to use our existing HA mechanism. We use the current active logs we have today, instead, but not the write ahead log of the key value store, which many of them actually provide, to persist the HDFS operations. So that way we require really minimal changes of the current HA mechanism, and which actually proven to work. Go next. So here's the current status of this project. So for phase one, we are implementing a namespace on top of the key value interface. So we are basically building a in-memory key value store. And nothing fancy. You can think of it as basically a hash map. And it's under active development under the Jira HDFS A2A6. So for phase two, we are actually storing the partial namespace into the memory. And that way we can store only the working set in the memory, and we put the code metadata on disk. That way allow us to really scale the namespace beyond the size of a name node heap. Go next. So I just told you about how we can actually implement the HDFS namespace on top of the key value store. So now I'm going to talk about how the performance numbers actually looks like. Does it actually works? Go next. So we do a little bit evaluation on a 4-node cluster. They are connected with 10 GB of network. Each machine has 2 core and 2 CPUs of a 6-core Intel CPU running at 214 gigs and 64 gigs of memory, and 1 terabyte disk running on Java 1.8. Go next. And we are comparing 3 instances. So one, the blue one is the Apache Hadoop 2.7 that is released like a month ago. The second is the namespace that is implemented on top of an in-memory key value map that basically corresponds to our implementation of phase one. And the third, the yellow one, is the namespace on top of the level DB. That would basically give us an idea of how things work if we actually go beyond the name node heap. Go next. So the first benchmark I run is the NM footprint benchmark. NM footprint benchmark is basically a micro benchmark to testing how well the name node behave. It basically swarms up a single name node, just hitting requests without any overhead or RPC serialization, etc. So we find out for write, which means it's like create, make DARs, and delete, and rename. The performance is actually comparable. We have an even better performance numbers on delete. That might due to that the current implementation of the key value store is incomplete. We do not handle quotas, we do not handle snapshot, but also might due to we actually have a simpler implementations because the way we architect the system. So it turns out all this write operation, syncing the AD logs is actually the bottleneck. So you can see most of the performance is really much the same. So can I go next? Go next, go next. Okay. So the other parts of NM footprint benchmarks is the read operations. So 2 operations are pretty useful or pretty critical in terms of HDFS. So one is open, when you open a file, get the information about the block location. The other is a list file status, like doing LS or getting file informations. So we find out if we use a unpatched level DB, we only achieve like 1/3 of the throughput comparing to the 2.7 Apache, Apache up to 2.7. So further profiling, find out there's a lot of contention inside the global log and the level DB when we do a get. So what we end up doing is we implement a log-free fast path of get that basically corresponds to the red one on the performance graph. That way we cover the performance, we cover most of the performance overhead. Can I go next? So another benchmark I ran is the YCSP benchmark. So YCSP is basically a benchmark that run against a key value store, which could be H-based, Cassandra, as other things. So what I set up the experiments like YCSP running against H-base, and H-base using the HDFS we have. So we enable source circuit reads just to match the production deployment. And the right part is the performance number of different benchmarks. So we are kind of slower we are successfully run all the benchmark. We are kind of slower, but just to, it is untuned, so it's kind of expected. But still, we are going to continue to investigate why it's slower. And can I go next? We also measure the latency of the YCSP benchmark. So in terms of latency, it's actually pretty much comparable. If you look at reads, writes, and scans, it's not much of a difference. Can I go next? So the other benchmark I ran is the Terrachelle. So Terrachelle is basically a MapReduce program that is I/O bounded, so it's not necessarily the greatest benchmark to be. But I just want to show that actually MapReduce program also works. And so I put up 10 GB for data per node. We have 3 data nodes. That means that we have 30 gig of the data in total. And if I run Terrasort, Terragen, and Terravalidate, it shows comparable performance, no performance degradations. Can I go next? So another interesting problem to talk about is we continue to say that we can put only the working set in the memory. So what happens if your working set is too large and cannot fit in the memory? So what is the performance impact when you have this kind of problem? So here's how the experiment is set up. So I run the NM throughput benchmark with the get file status, just as the previous slides, but I bound the size of a working set. So as you can see, between the size of the actual size of the working set should be between 128 megabytes and 64 megabytes. And once you hit that, you actually notice significant amount of performance degradations. Can I go next? Can I go next? Yes. So now I'm going to describe our future works, and then I'll conclude. So this is an ongoing project, and that basically means that a new architecture of a HDFS name node. It requires some implementation and requires time to actually get stabilized. But as we point out, we are going to have a fully compatible API, so the adoption cost will be pretty slow. There are questions that are unanswered at this point. So particularly, it's an operational concern. So for example, what would happen if we move to a key-value store? Some key-value store actually requires some sort of cleanup process. So for example, HBase requires a compaction, so as level DB. And what does FSCK we have today means? And another example is how to recover from failures, how we're going to put all this key-value store from here, because when we basically move beyond the name node heap, that we have a totally different value models. And the other problem is what happens when you bring up the name node. Since you are only storing the working set in the memory, you basically can say, I can bring up any name node at any given point of time, but you are going to have a lot of cache misses at the very beginning, which we basically call a cold startup. What does it mean for your job? So that's kind of the question that we have to continue to investigate and answer. Can I go next? Can I go next? 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 Okay, so just to conclude, HDFS needs to continue to scale to match our use case and the growth of the data. So this project basically proposed to evolve HDFS towards a key values-based architecture, which allow us to scale beyond the size of the name node heap. So we have a bunch of preliminary evaluation. The results looks pretty promising, and we do not have significant performance degradations. Obviously, we can do better, but still it's not, I think if we can continue to improve and get to the point that what we have today. And can I go next? Yes, so before I end in the talk, I would like to acknowledge, say thank you to 2 of our interns that with us. So Lynn actually did the POC of the LevelDB backend namespace, And Zhilei actually do the integration parts of the HDFS feature and level DB and some performance tuning. I would like to say thank you to these two awesome interns. And can I go next? Okay, that's all I have today. I'm ready to take questions. Thank you.
A question. So I also understand that there is effort to do federation for HDFS. I just wonder whether you have any comments on this effort related to the federation.
Yeah, so federation is obviously a way to scale your namespace, probably. I mean, the main difference is the federation is basically gives you a static partition of your namespace. And many applications does not work particularly well on this part. So for example, for Hive and many MR applications requires a rename from the temp directory to another directory and requires automaticity of this rename to actually make sure the program actually works. And if you do federations and you put the temp and the application into a different namespace, which many people actually do this way, that your application actually breaks. So we still find a lot of values in terms of having a single global namespace.
All right, so then can you comment on the status of federation? Is that work done, or is that also in progress?
I think federation is pretty much a stable feature,
Okay.
as far as I know.
All right, thanks.
Hey, Harvey. So what other key value stores are you targeting other than level DB?
For this particular one, okay, I'm going to stay away from that. Okay. So for this particular project, we are talking about level DB. And I would like to just highlight that we are not limited to one single key value store. It's more of a generic effort so that you can, and we basically design from day one to make sure we can plug in different key value stores.
So it's very interesting in general that key value interface to HDFS that you are building. I have two comments. First is that we're still going to be bound by a single name node performance. We'll scale the namespace, we'll have more objects because some of them will go into cold storage. But performance-wise, it's going to be mostly the same, and your benchmarks show that, right? So it's a little bit better, a little bit worse. And one strange benchmark with delete. Delete usually on throughput benchmark is the fastest operation in the name node. Mm-hmm. And yours was like 3 times slower than create.
No, I think it's the reverse, I guess. We are faster than the...
No. If you look at 270, right?
Okay.
And compare create with delete. Delete should be much higher throughput than create. I mean, a little bit. But in your case, it was 3 times smaller.
Yeah, I mean, I actually double-checked the result. I think I get it right. The reason why delete becomes really complicated is because when we introduce snapshot and quotas, we have to go through the whole trees, and there's a lot of complication behind the scenes, and that's probably my suspicion why delete is slower.
Yeah, we can take it offline, but
yeah, sure.
I just ran them on trunk, and deletes were faster.
Okay, cool. That was good to know. All right. So good. Thank you.